what I'm going to do is I'm just going to have a look at question 2B off your functions assignment and just give you a slightly alternative approach to how one might solve it if you're trying to evaluate an inverse. So I guess the thing about this is that if you look at 2B, finding the inverse of f and finding the inverse of g, like finding the inverse functions, would be useful if you had to do multiple evaluations, because you'll have a general function, right, that will describe the inverse of f, and a general function that will describe the inverse of g, and therefore you can work out f of minus 1 of 18, or f of minus 1 of 27, or f of minus 1 of 0. So working out the general function is a good thing to do. But if in the grand scheme of things, all you have to do is find one value, in this case, what's f of minus 1 of 18, and then what's g of minus 1 of 18, then maybe you don't have to go to all that trouble. So we're trying to work out f of minus 1 of 18 is, and we know that f of x is equal to 3x. Yeah? Now, remember that the inverse maps the output of f to the input of f, yeah? It swaps it over. So what we could do instead is we could say, let 3x equal 18, the output, therefore x is equal to 6, therefore f of inverse of 18 is equal to 6. Parrot, come grab this. Does that make sense? So basically, since I'll kind of just go for it graphically. I'm inputting 18 to f of minus 1, and I'm getting something out. But that's the same, because of the way it works, of putting the input into f and getting out 18. So all I'm doing is I'm using that fact. And instead of inputting x and getting something out, I'm inputting 18. Does that kind of make sense? So it's a really handy feature, because you can see that that's a lot less work. That's a lot less work than finding the two inverse functions and then going from there. Similarly, I can go for g of minus 1 of 18, I can say, well, g of x is equal to x plus 2. Yep. And that has to equal 18, therefore x equals 16. Then, now you have to show that f of minus 118 plus g of minus 1 of 18 is equal to 22. So here's a slightly fancy way of doing it. You say left-hand side equals f of minus 1 of 18 plus g of minus 1 of 18. So that's what LHS stands for, the left-hand side of the equation, which equals 16, oops, better do it the right way around. 6 plus 16, which equals 22, which equals the right-hand side. And then you could say, quo erat demonstratum, thus it is proven, or thus it is shown. Okay, so that's how you do that particular question. Well, that's one way you can do it. Now, everybody, I've never shown you that method, so I wouldn't expect anyone to have done that. But everybody did it by working out the inverse functions first, and then substituting in, and then evaluating to 22. Some people did some funny old things with the way they did their setting out to show that, blah, 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 equals 22. But you got there in the end. But I think that's the most schmick way of doing it. Basically with any show that or prove that, you basically want to show that you stick with one side, left or right hand side, and you manipulate that side until you get it to the other side, and then you say QED. Okay, and just trying to think if there's anything else I wanted to show you. That kind of idea though could be used in a bunch of the questions in this little homework assignment. I think that's basically it from my perspective. Does anyone have anything particular you'd like me to go through before we move on to today's lesson? Okay, so that's in Mark's book now. It's the PDF in Mark's book. I haven't put any more comments in Mark's book. You have got a couple of ratings there, one for communication and the other one for knowledge and understanding. So that's in Mark's book as well. This one is for you to keep, but obviously if you lose it, then it's in Mark's book for you to, sorry, in the assessment part. We call it Mark's book as a teacher, in the assessment part of Sector Engage. Alrighty, so we'll move on to today's lesson unless you've got any last minute thought questions. Okay. So in Friday's lesson, we started our exploration of exponential functions. We introduced ourselves to introduced where exponential functions can be utilised where geometric sequences can't. We saw the pitfalls in geometric sequences when it came to continuous data versus the discrete counting data of a geometric sequence. We also saw that there were problems with exponential functions when it came to negative bases. And then we spent the rest of the time looking at exponent or index laws, reminding ourselves that the big number is called the base, and a base is raised to a power or to an index or to an exponent. And I would argue that exponent probably is the most common word to be used worldwide, although in the UK and Australia, index is very common. Guess which one's older? Exponent's older. Exponent's older. Not by much though. Exponent comes from some dude in the 15th century, and then maybe 50 years later the word index came through by an English dude. Anyway, so you can use those words interchangeably, more or less. So we went through the index or the exponent laws. By the time you get to the end of year 10, you should have at least been exposed to these laws. It's okay if you weren't, because we went through them all. I've got a video on it already, so I'm not going to bother dwelling on it. And the last thing you were asked to do is to try exercise 9A and 9B, which I'm hoping you will have. I got the impression that most people had done most of that by the end of that lesson on Friday. That's not the case. Then just do some catch-up time. P.S. while I'm thinking of catching up and stuff like that, I'm starting to get homeworks in, which is great. You do have until Thursday to have that homework done. Don't forget to get that homework done. I'm not expecting anyone to get it done before Thursday. Okay, so that is that. We're going to have a look at exponential equations now. So generally speaking, so far, I mean, unless you've seen it in another course, but I'm just saying, generally speaking, in our mathematical journey, the unknown that we're looking for has tended to be not in the power. Okay, so you've either got something like this, and then you solve for x. Not this one. No, isn't it? It's still a number. Solve for x, or it might be like this, and solve for x. So there's a power, but the power is an actual number. But I guess the question is, what happens if we go like this, and we have to solve for x? Now, x is now in the power, in the unknown. The x is in the power instead of in the rest of the equation. So what we've already come across this, haven't we? We've come across this in our geometric sequences unit when we had to work out the number of terms. Okay, so it's not an unknown. If you remember the basic way of doing it, well, you know, the way we just fudged, I suppose, is to work out the log of both sides. But the problem with that is that you need one of two pieces of equipment in order to work out the log of both sides. One is a calculator, or two is a logbook. And logbooks are so old, even I didn't have to use them when I was at school. I had calculators when I was at school. I'm not that old. It's very rude for you just to sit there and just nod. Really? That's interesting, Richard. I thought you would be that ancient. Rude. Okay, so what I want to do is And in fact, the purpose of this day, really, this lesson, is to look at the method by which we solve an exponential equation without using calculators. There's really only one method, and it doesn't work when you get to anything even slightly complicated, really, that you have to use your calculator. So if the answer is, x equals 3.2, you've probably got there via your calculator, right? So we're talking about whole numbers or simple fractions, normally. That's, that's a bit of an exaggeration, but it's reasonable. So let's start with a really simple example. I think it's the easiest way to do it. Feel free to write these down as board notes, because that's what they are. Either you're ready already or you're not going to do it. So really simple example. If I have 2 to the power of x minus 1, and I'm told that's equal to 2 cubed, then I can say that therefore x minus 1 is equal to 3. This is called, I'll keep it for, I was going to say alliteration, but I think alliteration is only when it's a consonant, isn't it? I'll keep it for the assonance. Equating exponents. I'm pretty sure assonance is when you have a repeating vowel sound, I think.
I think if it's at the start, it's still alliteration.
Is
it? Maybe. Because assonance is like the vowels in the middle.
Is it?
Yeah.
Isn't it rhyme inside like the one? Isn't that assonance?
Assonance is repeating vowel sounds, but they can be assonance.
Okay. I'll look it up. You know I'll look it up later. Okay. So this step is almost always, I can't think of a time where it wouldn't be. This is what we need to do. We need to get the equation to the point where you've got a base to a power on the left and the same base to a power on the right, so that we can equate the exponents. And once we can equate the exponents, we can then solve for x like we have done since grade 8 or so, if not earlier. I added 1 to both sides. Is that okay? That's basically it. So what I thought I might do is just take you through a whole bunch of examples where we're just teasing that out. You can basically try and get ahead of me if you like. I'll give you a moment to do so each time. So just a whole bunch of examples. I don't think it's worth writing big, long, complex notes about it. I think the examples would be good enough. So let's say we've got 3 to the power of x plus 1 is equal to 27. Now, on the left-hand side, our base is 3. On the right-hand side, our base is 27. 27 to the power of 1. But we can change the right-hand side so it's the same base as the left-hand side. Why is that, Siggy?
You can change the left-hand side.
No, leave the left-hand side.
Sorry.
We can change the right-hand side so it's the same base as the left-hand side. So how are we going to change the right-hand side?
You're going to change it so that it's like 27 root 3 kind of.
Not 27 root 3, because that would actually be literally changing the value, right? 27 times root 3 is not the same as 27. Thank you. So when I say change, I mean change the form of it without changing the value of it. 27 root 3 would, of course, change the value of it. Aaron?
3 to the power of 3.
Yes. So what we really want to do is we want to say 3 to the power of what equals 27? And the answer is 3 to the power of 3. So we now have left-hand side equals right-hand side. We haven't changed the value, but now we have agreement in the basis. So therefore, x plus 1 is equal to 3, and x is equal to 2. I took away 1 from both sides. We've got to the point in our mathematics where I hope I don't have to spell out little fundamentals like that. Any questions on that one? Does that kind of make sense? So we're just doing whatever we can to manipulate without changing the value. It's a really good, I'm glad you said that, Siggy, because it helped me emphasise that. Okay, 2 to the power of, so example 3, Give you a moment to think about it. 2 to the power of x plus 1 equals 4 to the power of x plus 1. These bases are not the same. They're not the same. Give you a moment. You can talk to the person next to you if you like. I'll give you a moment to get ahead of me. Remember, the name of the game is to have base to the power on one side, same base to the power on the other. I'm videoing this, so I should put some waiting music in the middle. It's been good when you're watching this back. Okay, how did we go?
This is -1.
I just want the next step. I don't want a solution. I want the next step. Elizabeth, what did you do?
Put 2 squared into brackets.
Perfect. Instead of the 4. That's exactly right. So we have 2 to the power of x plus 1 on that side, and Elizabeth recognised that 4 can be written as a base 2 number, 2 to the power of 2. Excellent. Now, Rose, what did you do after? Did you do that? What did you do next?
Multiply x plus 1 by 2.
Excellent. You can see why we need those index laws to start with, right? Or the exponent laws to start with. So Rose identified the right operation, which is to multiply each bit on the outside, x plus 1, by 2. So you should have got 2 to the power of 2x plus 1.
Plus 2.
Thank you. That was not a deliberate mistake, it was just a brain fade. And now we can equate the coefficients and solve, right? So x plus 1 is equal to 2x plus 2. So that means that I can subtract x from both sides to get x over here, and I can subtract 2 from both sides to get -1 over here. And I'm done. X equals -1. -1 is the same as x, is how I was meant to read that left to right. But I'm done. Is that okay? Questions? All right. So we do whatever we can to get those bases in agreement. Example 4. Or example 2 squared. There we go.
Ugh.
The thing is, you might not know yet your approach, or maybe you do, but it kind of looks like it must work, doesn't it? You know that 3 squared equals 9, so it feels like as if you can get somewhere, but can you?
Oh, okay.
Same base on both sides.
That makes more sense now.
Would it have to be a negative number?
It will be.
Never mind.
Okay, this is a bit trickier, so I'm wondering what people have done. I'm not going to just pick on someone. Who'd like to say what they did next? Go, Rose.
3 to the power of -1.
Close.
3 squared.
Sorry, -2.
Oh, sorry.
No, 3 to the power of
I think you're
-1.
trying to give me the answer.
No, I'm saying I'll turn 1 over 3
Yep.
into 3 to the -1.
Okay, yeah, that's cool. I probably would have done it in one step, but
Oh,
That's
yeah,
fine.
and then do it by x.
that's absolutely fine.
Equals 3 squared.
Not quite. Oh, equals 3 squared. Yep.
Yeah, so then negative x equals 2.
I probably would have gone straight to that line. This
Oh, yeah.
line here would be fine. It's okay if you don't though.
Yeah, sorry, I thought you wanted to.
No, it's all good, all good, all good. Yeah. So it'd be okay to say that 1 on a to the power of x is the same as a to the power of negative x. It's okay to do that in one step. So therefore, I think the rest is trivial. X is equal to -2. Any questions on that one? Yep, okay, getting a few nods around the room. Okay, next example.
Sorry, I just got it.
3 times by 2 to the power of x plus 1 is equal to 12. Name of the game. The name of the game is to get those bases equal.
It's not 3 times 2 squared. Two squares 4.
Why did you remove okay, why?
Okay, I've prepped Lily to give you the answer for this one, or to go through the solutions. What'd you do, Lily?
I changed the 12 to 3 times 2 squared.
Okay, just hold there for a second.
That's what I did.
Is everyone okay with that? Okay, that's not the way I would have done it, but it's still a very legitimate way of doing it. Because now we've got the left-hand side form the same as the right-hand side form, which means we could say, therefore, x plus 1 is equal to 2 and x is equal to 1. Okay? Good. Absolutely legit. I'll just go the way that I would have done it, only because it's sometimes a little bit more applicable to more situations, you know what I mean? So this is not saying that you're wrong, Lily. What I would have, as a general rule, what you want to do is divide out the part that's not the base. So if you divide out the part that's not the base, you'd have 2 to the power of x plus 1 on the left. Actually, I'll squish it in. Do it in 2 lines. 2 to the power of x plus 1 is equal to 4. 2 to the power of x plus 1 equals 2 squared, and then you can go from there. Even with calculator work, when you're using logarithms, you want to divide out the bit that's not the base first, as a general rule, which is why I'm putting it there. Okay, but your solution was definitely legit. Sorry, that was example 5, and I accidentally didn't write the heading down. One more. Example 6. Example 6 is 5 to the power of 3x minus 1 minus 1 equals 0. I'll pause the video and give everyone a chance to get ahead. 7.2. No, I just said that just to annoy people who just came back on the video. Okay, so 5 to the power of 3x minus 1 minus 1. So I've been around everybody, so I think most, if not everyone's got the right idea now. We add 1 to both sides, and the trick I wanted to show you here is to remind you that 1 is anything to the power of 0. So we can easily write that as 5 to the power of 3x minus 1 equals 5 to the power of 0. Therefore, 3x minus 1 is equal to 0, and x is equal to 1/3. 0.3 recurrent. Okay, that's it. So that's the 6 examples, and I don't think I need to belabor it anymore, but I think I'd really like you to practice doing these. It's 9:06 now, so what I've got for you here might not even take you the whole 25 minutes, I'm not sure. So it's exercise 9C. It's just a small exercise, so I want you to do them all, and they're on page 401. And I think that should be enough for you to get a feel for these initial equations or exponential equations. Again, with the idea that if they were any more complex than this, odds are you're going to use a calculator and your log rules or your log functions to do it. All right, I'll stop the video here.